Okay, so in today's lecture, we are going to talk about very basic point processing operations like mathematical operations and logical operations. Okay, so let us start the slideshow. Okay, so under mathematical operations, we will be having a look at what is image addition, what is image subtraction. So basically, we can add any two images. Say F1 XY is one image, F2 XY is another image. Then simply by performing point by point arithmetic addition, we can get processed image that is GXY. Okay, now here what is range of gxy? It depends on how many bits we are using to represent the image. So if we are using 8 bits per pixel, we can get maximum value that is 255. If we are using 16 bits per pixel, maximum value will be 2 raised to 16 minus 1, that is 65535. For 32 bits, range is as shown here. And if we go for 64-bit operations, that is 64 bits per pixel, range is as shown here. Okay. So we can add two images by pixel addition. So we can add pixel at location x1, y1 from image f1 with pixel at the same location, that is location x1, y1 from image f2. And when these two are added, we get new pixel at location x1, y1 for the new image G. Okay, so this is basically pixel by pixel addition. Now, another type of add operation is as shown here. We can add any constant value to all the pixels for the given image. So, if your image is f1xy, f1xy plus some constant k gives you another image, processed image gxy. Okay. So here constant k is added to each and every pixel from image f1. So this is simple image addition operation. So here you can understand how we can perform pixel by pixel addition for two images. So if your, say this is your image A which has size 4 by 4. This is image B which has size 4 by 4, 4 rows, 4 columns. Now we can perform pixel by pixel addition. So this is very first pixel 7. It is added with uh, pixel at same location from image B to get the result as 14. So 7 plus 7 gives you 14. Then next pixel 3 plus 3 gives you 6. Then 3 plus 3 gives you 6. 1 plus 1 gives you 2. Okay, so this is pixel by pixel addition. So this is very simple operation. Now here what is important is that the two images that we are willing to add, they should have same size. Then only we can perform pixel by pixel addition. Okay. So here image A has size 4 by 4. Similarly, image B has size 4 by 4. Okay. So this is simple pixel by pixel addition. Okay. Now we one important thing here is, say in this example, say if we are using 4 bits per pixel to represent the image, say no, we are using 4 bits per pixel. Okay. Now when we are using 4 bits per pixel, we can have total 16 gray values ranging from 0 to 15, right? Maximum gray value can be 15. Okay, so maximum gray value is 15. So if we are using 4 bits per pixel, whatever result we are getting after addition, we can use it as it is. Now, instead of 4 bits per pixel, if you assume that you are using 3 bits per pixel, if you are using 3 bits per pixel, what is the maximum pixel value possible when we are using 3 bits per pixel? Please type your answer in the chat box. What is the maximum pixel value? Yes, all of you have given me correct answer. The maximum pixel value is 7. Aryan, Sharan, Pranav, your answers are correct. Okay. So maximum value is 7. So after addition, if you observe here for very first column, we are getting value which is greater than 7, right? 14 is greater than 7. So if we are using 3 bits per pixel to represent the image, in that case, all the values above 7, those are truncated to 7. So after addition here, actual addition is 14, but because of limitation of 3 bits per pixel, here instead of 14, we will get it as 7. Okay. So here, what is important is whenever we apply any image enhancement operation, after performing actual operation, we should go for range normalization. As we have studied in previous lecture, we can perform range normalization to the desired range. Okay. So after addition, say you are getting the result in the range 0 to 14. So after addition, you need to apply range normalization so that all your results will be converted to range 0 to 7. Okay. So otherwise, if you don't apply this range normalization, by default, only higher values, those will be replaced by 7. Okay. And all other values remain same. But if you perform range normalization, your entire range 0 to 15 will be mapped to 0 to 7. So instead of 6, here you will get some smaller number, okay, because of range normalization. And effectively, you will visualize the correct image, okay. So this range normalization is very important, okay. So this is simple addition operation. Hope it is clear to all of you. Now here one example is shown. So here this is image A and this image B. Image B, in image B there is some granular noise. And if we perform addition of image A with image B, you can get this image. Image C is result of adding image A with image B. In image B, there are many white areas that are brightest areas, those are also added to original image. So overall, you can observe that this image is brighter than the original image, along with some dark dots on it, which are present in image B. Okay, so if you add image A with image B, this is resultant image. Okay, then if you add some constant, say constant 50 to original image, you are getting this result which is shown in result D. Okay, so this figure D is after adding a constant value K to the original image, and here K is considered as 50. Okay, so as we are adding some number to each and every pixel value, every pixel is becoming brighter than the original. Okay, so that's why your resultant image displayed in figure D is brighter than the original image A. Okay. So these are examples of applying addition operation on the given image. Okay. So how this addition operation is useful. So basically this addition operation can be used to perform, say, basically filtering or for removing noise. So basically, if your image is corrupted by, say, zero mean noise. What is meaning of zero mean noise? If we take average of the noise over certain duration, it comes out to be zero. That is meaning of zero mean noise. Okay. So in order to remove this type of noise, what we can do is, instead of capturing single image of the desired object, we can capture multiple images of the desired object. Say this is your desired object. So instead of single image, we can capture, say, 10 images of the object, say I1, I2 up to I10. Okay, so we can capture, say, 10 images of the object, and then we take average of these 10 images by pixel addition. So we can add I1 plus I2, I2 plus I3 up to I10. We can add all these 10 images of the same object, okay, and then divide it by 10 to get an image where noise is removed. Okay, so this is simple application of image addition. So for the given object, we can capture multiple images and we add those images and we take average. And because of averaging over greater number of images, that zero mean noise, it is removed, or it basically reduces to a small extent. In ideal condition, it won't be removed completely, but it will be reduced by great extent. Okay, so this is simple application of image addition. Now let us have a look at next point processing operation. So it is image subtraction. So the subtraction of two images can be done as follows. So if you have image F1 and image F2, we can obtain image subtraction by pixel subtraction. So F1 XY minus F2 XY gives you a processed image GXY. Okay. And when we apply image subtraction operation, there is possibility that you are getting negative answers, right? Say if your pixel value at location XY in F1 is say 0, and pixel value at location XY, same location in image F2, if it is 100, 0 minus 100 gives you minus 100, right? So there is possibility that you get negative results. So many times in many applications, we are simply interested in amplitude of the difference. Okay. So whenever we are interested in amplitude of the difference, we can take modulus of the difference. We can neglect the sign of the result and we simply consider modulus of the difference. So for image subtraction, wherever needed, we can consider modulus of F1 XY minus F2 XY. Because when we consider simply magnitude part, it becomes easy to display the difference as an image. Okay. So for image subtraction operation is usually followed by modulus operation as shown here, where we consider simply magnitude part of this difference value. Okay. So here there is an example in numbers to understand image subtraction operation. So this is your image A, this is image B, and we can perform point by point subtraction as shown here. Okay. So as shown here, we can perform point by point subtraction. So 14 minus 7 gives you 7. Say 6 minus 3 gives you 3. 6 minus 3, once again we get 3. Then 2 minus 1, we get 1. And same process we can apply for each and every pixel from all next rows. Now, if you look at this particular pixel, this value is 2. 2 minus 14 gives you minus 12. Similarly, if you look at this first pixel from last row, it is 1. 1 minus 7 gives you minus 6. So for these two locations, we are getting negative results. Okay. So if we are simply comparing the two images, okay, so we can also consider magnitude. We can simply consider magnitude of the difference. Okay. So if we consider magnitude, in that case, this minus 12 will be displayed as 12 and minus 6 will be displayed as intensity value 6. Okay. So this is meaning of modulus of uh, g of xy. Okay. And if you are not interested simply in the difference or simply in the magnitude, like we applied range normalization after addition, we can follow the same technique here. After, say you are using 4 bits per pixel to represent the image. For 4 bits per pixel, your desired range is 0 to 50. But after image subtraction, for this particular example, we are getting range from minus 12 to 7. Okay. So this range minus 12 to 7, by using range normalization technique, we can normalize it between 0 to 50. Okay. So after subtraction operation, we can apply range normalization so that you can display it as an image where you can get idea of the difference. Okay. So when we want to display this difference image as an image, we need range normalization after image subtraction operation. Okay. So we can check what is the range of the resultant image by determining maximum negative number and maximum positive number. So that gives you range, which is in this case, it is minus 12 to 7. And then you can apply range normalization technique to convert it between 0 to 50. Okay. So this is image subtraction operation. Now here one example of image subtraction is shown. So this is your image A and this is your image B. Now if you compare these two images, you can easily understand that only this particular portion, which is black in second image, is different in these two images. Okay, so it is easily identified by subtracting image B from image A. Okay, so when we subtract this pixel by pixel, we can easily understand that all the pixels except this portion, they are identical. Okay, so when we subtract, say, pixel value 200 minus 200, we get result 0. Okay, so except this portion, everywhere else we are getting value 0, okay, which is indicated in the result C, okay, and only for this particular portion, whatever your original pixel value minus 0, right? This black indicates 0 value. So original pixel value, say this is 200, 200 minus 0 gives you value 200. Okay, so only for this portion, your original data from image A is written. Okay, so this is an example of subtraction. Okay, so only at this portion where there is black in image B, in image C, we are getting original image contents from image A. Okay, because we are effectively subtracting simply 0 for each of the pixels from this particular portion. Okay, so this is image subtraction operation. Okay, then this next image, result D, it is obtained by subtracting a constant. Like we add a constant to one particular image, we can also subtract constant from the given image. Okay, so here from the given image, we are subtracting constant value 50 from each and every pixel. So we are reducing each pixel value by 50. So that's why if you compare this result D with result with original image from figure A, we can easily observe that this result is slightly darker image than the original image, because we are reducing each and every gray value by 50. Okay, so this is subtracting a constant from the given image. Okay, this is one more example. This is image A and image B, and this is result of subtracting image B from A. So in image A, there is no coin at this position, and in image B, there is no coin at this position. And these two are identified as after differencing, taking difference of A and B. So basically, this simple mathematical operation, that is image subtraction, is very useful for image comparisons. It is useful for object detection. It is also useful in motion detection when we consider a video. Okay, so say in an image you have one particular ball in at one position, and if that ball is moving at in a video, then simply by taking difference of one frame with respect to previous frame, we can identify motion of that ball. Okay, so this simple image subtraction operation is very useful for many applications like identification of motion. Then it is also useful in image compression. So again, while compressing the videos, we can take difference of frame, one particular frame with respect to previous frame, and we can simply code that difference, or we can code the new information from every image, and it leads to lots of amount of compression. Okay, so this simple mathematical operation is very useful. Then let us have a look at another operation, that is image multiplication. So as shown here, multiplication of two images can be given as shown here, f1xy into f2xy. Again, these are pixel by pixel multiplications. Also, we can multiply an image by a constant, say k. K into fxy gives you multiplied image gxy. Okay, so this particular result is obtained by multiplying this original image by a constant value, say 1.25. Okay, so here if we multiply original image by 1.25, we are getting this image which is slightly brighter than the original. Because of multiplication by 1.25, every pixel value is brightened. Okay, similarly, we can have image division operation. Okay, so we can divide two images as shown here. F1xy divided by F2xy gives you processed image gxy. Again, like addition or subtraction or multiplication, this division is pixel by pixel division. We divide pixel value at location xy from image F1 by pixel value at same location, that is location xy, from image f2. Okay, so this is image by image division. We can also divide an image by a constant. Fxy divided by a constant k gives you image gxy. So each and every pixel from image fxy we divide by same constant value, say k. Okay, hope you are getting these operations. These are very simple operations. So here an example is shown. Okay, so this is image A and this is image B. Now simply consider image B, and this is image C. which is usually called as a mask because this is binary image. Here inside the ellipse, whatever portion is there, it has value 1, and outside the ellipse, whatever portion is there, we can call it as background, value is 0. Okay, so a binary image of this form, we can call it as a mask. Okay, so this white portion represents value 1. Okay, so this very first image is result of the image which is obtained by dividing uh, previous image by 1.25. So this image, which is image into 1.25, it is divided by 1.25 so that you get original image. Okay, so this is example of dividing an image by some constant, and we are getting this result. Every pixel value is divided by 1.25. Now let us consider this image B. Okay, so this is your image 1, and this is your binary image, which we are calling it as mask. Now when we multiply these two images, when we perform multiplication of image B into image C, we get this result, right? When we multiply any pixel value by 0, of course we are getting 0. Okay, so here outside the ellipse, we are getting all the values, pixel values as 0. And inside the ellipse, this mask value is 1. So when we multiply pixel values by 1, we get original pixel value. So if in image D, result D, if we look inside the ellipse, whatever values we have, those are from the original image, image B. Okay, so ellipse is positioned here, and as we are multiplying all these pixels by 1, we are getting this value. Okay, now let us look at last image, which is image E. So this image is obtained by this image 3, that is result D, divided by original image. Okay, image 3, image from figure D divided by this particular image from image B gives you this result. So how we are getting this result? See, in image D, outside the ellipse, we have all 0 values. 0 divided by any number, of course, will give us result 0. So outside the ellipse, we are getting 0. Now inside the ellipse, whatever pixel values are there, those are identical to pixel values from this image B. So a number, say 200 divided by 200, it always gives us 1. Okay, so inside the ellipse, we are dividing respective values from image B, and it results in 1. So that's why this image 3 divided by this image 1 gives us image 4 as shown here. Okay, so inside the ellipse we are getting values 1, outside the ellipse we are getting values 0. So this is simple image division operation. Okay, now let us have a look at some logical operations. Okay. If you have any query, please type it in the chat box. Okay. Till this stage, I hope all of you have understood these simple operations, mathematical operations. We had a look at addition, subtraction, multiplication, and division. Okay. Now let us move to next set of point processing operations. Those are logical operations. So as these are logical operations, we are going to consider binary images, which are represented by only two levels, 0 and 1. And of course, there is only one bit per pixel. Okay. So these are some logical operations that we can apply on the image. And NAND or NOR. We can apply XOR or XNOR. We can also invert an image, or we can apply NOT operation, logical NOT operation on the image. So these operations are very similar to your basic logical operations. Okay, so let us consider this image A and image B. These are, say, your original images. This is image A and image B. Now, can you tell me what logical operation between A and B gives you result C? Try to guess this logical operation between A and B. We have performed some logical operation between A and B. And after this operation, we are getting, say, result C. Okay. Okay, so here, yes, I'm getting few answers, but I think these answers are not correct. What do you mean by logical and? If all the wherever we have uh, one value, logical one in common between these two images, we will get a one. Wherever images are not matching, we will get a zero. Okay. So yes, Vikrant, your answer is correct. It is logical or operation. This image C is result of logical or operation, because here or operation or the two images means if both the images have one value, we get one. If any of the image has one value, we get a one. Okay, so this image C is result of logical or between image A and B. And if you look at image D, it is logical and operation between A and B. So here we are getting this portion round here, because few points from this rectangle, those at in image A, at those position, pixel value is 0. So 0 ended with 1 gives us here 0. Okay, and only common portion between A and B, common white portion, is displayed here as white. Okay, so it is simple bitwise ending between A and B, and this gives you result D. This is logical AND operation. And can anybody guess what this operation is? Again, between image A and B. What is this logical operation? Can anybody guess? This is exclusive OR operation, because common portion between A and B has value 1, right? So 1 XORed with 1 gives you 0. Similarly, 0 XORed with 0 gives you 0. 1 XORed with 1 gives you 0. And wherever your input bits are different, that is 1 XORed with 0 gives you 1, 0 XORed with 1 gives you 1. Okay, so this is exclusive OR operation, and this is result will look like as shown here. Yes, Sharon, these logical operations are bitwise operations, and for these images, we have assumed that these are binary images. So wherever binary value is 1, it looks white in the image. And wherever binary pixel value is 0, it appears black, as black in the given image. So black portion is equivalent to 0 value. White portion is equivalent to 1 value. Okay. So this is result of XOR operation. Okay. Now, instead of images, you can try to understand these operation as operated on arrays of numbers. Okay. So say this is your binary image A. This is your binary image A, and this is binary image B. Now tell me what is result of ANDing A with B. Just you can describe me the result. What is result of ANDing A with B? Please type your answer in the chat box. A ANDed with B. You can describe the result in one line. A ANDed with B. You can call these as rows. You can call these as columns of A. So if we AND A with B, just go, as I'm not getting any answer, I'm explaining it. 1 ANDed with 0 will give you 0, right? It will give you 0. Similarly, 1 ANDed with 1 will give you 1. Then 0 ANDed with 1, 0. 0 ended with 1, 0. Yes, Vikrant, I got at least one correct answer. Vikrant, your answer is correct. Okay. So first row will be 0, 1, 0, 0, and all next rows are identical to first row because all these, both these images are row wise identical. So we can say that if we AND A with B, we get only one column, that is second column will be 1, all other bits will be 0. Now try to give me result of A ORed with B. Please type your answer in the chat box. If we OR these two images, that is the second operation, A or B, what will be the result of A or B? Yes, Aryan, your answer is correct. What about others? What is result of? Yes, Vikrant, your answer is correct. So when we OR these two images, we will get all bits as 1. Okay, because here in first column A is 1 and though B is 0, A is 1. So result will be all bits from column 1 as 1, and for rest 3 columns your B is 1, though there are 2 columns at 0 in image A. Okay, so if we OR A with B, we will get all bits as 1s in the resultant image. So this is your result of A or B, and this is result of A and B. So hope logical operations are clear to you. Now in these logical operations, we have considered binary images. If your image is gray image, okay, in that case, how to apply these logical operations? If you have gray images, you have to represent all pixel values as binary numbers and then perform binary bit by bit logical AND or logical OR. So consider that, say you have one pixel value as say 6, okay, and another pixel value as 7. So you need to represent it in binary format as 111, say using 3 bits per pixel, and this 6 will be 110. Now if we want to apply AND logical operation, and bit by bit ANDing of 7 with 6 is done, and final result will be same as 110. Okay. So if you have gray images and if you want to apply logical operation on it, in that case, you need to represent those gray values as binary numbers and apply bit by bit logical operations on these numbers. Okay. So basically these uh, logical operations are used to mask certain portion from the given image. So as shown in previous example, that is this example. So if we apply logical AND operation between these two images, okay, so this image, when we logically AND with image B, we can get this image. So to select certain portion from the given image, we can make use of logical operations. Okay. So these are very simple logical operations, and with these operations we have completed all point processing operations, and now we are going to start with